Geometry of curved space, vectors and the metric tensor. Gravity originates from the curvature of spacetime caused by massive energy sources. Different gravitational sources, the sun, black holes, and beyond, each curve spacetime in their own way. The left-hand side of the gravitational field equations captures this curvature, and deriving it is the goal we are working toward. What does it mean for spacetime to be curved? Consider the surface of the Earth. We feel as though we are standing on flat ground, and it seems that parallel lines should never meet. Yet if two people set off from two different points on the equator, walking in parallel, they will eventually meet at the North Pole. This is not because they were drawn toward each other. It is because the very ground beneath their feet, spacetime itself, is curved. Now let us build the geometry of curved spacetime, that is, its mathematical description. Here we have a sheet of two-dimensional Euclidean space in Cartesian coordinates. The basis vectors Ex and Ey are defined uniformly across the entire space, each with magnitude 1 and oriented at 90 degrees to each other, forming a grid that extends throughout all of space. In other words, the same basis applies everywhere. Now let us place this sheet onto a hilly surface. Once placed onto the hilly surface, the angles of the grid are no longer 90 degrees, the edges become distorted, and their lengths vary from place to place. A curved space of this kind is called a Riemannian space. Now let us make the coordinate intervals on the curved surface infinitesimally small, and zoom in on a particular region. When the coordinate intervals on the curved surface are made infinitesimally small, each cell of the grid can be approximated as a parallelogram. Unlike Cartesian coordinates, the angles are no longer 90 degrees, and the side lengths differ from cell to cell. This means that a different basis is needed for each cell. In other words, the basis itself changes from place to place. Within each region approximated as a parallelogram, we can introduce oblique coordinates. We will now consider how to express vectors in these oblique coordinates, extending the approach we developed for Cartesian coordinates. In Cartesian coordinates, a vector is defined using components and basis vectors as A equals AX plus AY. The unit basis vectors Ex and Ey each have magnitude 1 and are orthogonal to each other. The components represent how many times each basis vector is multiplied. Furthermore, a component can be extracted by taking the inner product of the vector with the corresponding basis vector. Next, let us look at how the components are determined. The line segment that defines the Cartesian component Ax can be interpreted in two ways. It passes through point P and is perpendicular to the x-axis, or it passes through point P and is parallel to the y-axis. In Cartesian coordinates, both conditions are satisfied simultaneously, so they give exactly the same coordinate value Ax. In oblique coordinates, we adopt the same method as in Cartesian coordinates, a line passing through point P perpendicular to the x1 axis, or a line passing through point P parallel to the x2 axis. In Cartesian coordinates these two conditions gave the same component, but in oblique coordinates they give different components. The components written with superscripts, A1 and A2, are called contravariant components, and those with subscripts, A1 and A2, are called covariant components. The basis vectors with subscripts, A1 and A2, are called covariant basis vectors. For the contravariant components, triangles OSW and OA1P are similar, giving us. This means that the contravariant component A1 is expressed as a scalar multiple of the covariant basis vector A1. The same holds for A2 and A2. Therefore the vector A can be defined as for the covariant component A1, obtained by applying condition, a line passing through point P perpendicular to the x1 axis, triangles OSW and OA1P are not similar. Therefore A1 cannot be expressed as a scalar multiple of the basis vector A1. The same applies to A2. We therefore introduce a new set of basis vectors corresponding to the covariant components. We now define new basis vectors B1 and B2 whose geometric relationship with the covariant basis vectors is given by these basis vectors, written with superscripts, are called the dual basis vectors, or contravariant basis vectors. This diagram shows vector A expressed using the contravariant basis vectors and covariant components. Let us verify that each component is indeed a scalar multiple of its corresponding basis vector by checking A1 and B1. This diagram illustrates how the covariant component A1 is expressed as a scalar multiple of the contravariant basis vector B1. Please pause and take your time to verify this for yourself. Using the newly defined dual basis vectors and covariant components, vector A can now be written as This diagram illustrates vector A expressed in two different ways. Please pause and take your time to verify this for yourself. We approximated Riemannian space with parallelograms and introduced oblique coordinates. This gave us two types of components, contravariant and covariant, and we were able to define vectors as scalar multiples of the covariant and contravariant basis vectors respectively. Let us now express these using Einstein's summation notation, which we introduced earlier. Recall the rule: when the same index appears as both a superscript and a subscript within the same term, we sum over that index and omit the summation symbol sigma. These indices are called dummy indices. In 2 dimensions they run over 1 and 2, and in 3 dimensions over 1, 2, and 3. The choice of letter for a dummy index is arbitrary. In general, Roman letters are used in Euclidean space and Greek letters in Riemannian space. In Euclidean space with Cartesian coordinates, we were able to extract components by taking the inner product of a vector with a basis vector. Let us now examine the relationship between vectors and basis vectors in oblique coordinates. We begin by taking the inner product with different basis vectors. The calculation steps are shown on the next slide, so please pause and take your time to verify. Metric tensor. In the vector A, we were able to extract components by taking the inner product with different basis vectors. This was possible because the relationship between the basis vectors was defined using the Kronecker delta. What happens when we take the inner product of the same basis vectors with each other, that is, ai.aj and bi.bj? Let us work this out. Metric tensor. Let's take the inner product of the same covariant basis vectors. Here, We express the inner product of covariant basis vectors as follows, and call this the covariant metric tensor G mu nu. Taking the inner product of vector A with the covariant basis vectors allowed us to extract the covariant component AI. A dot AI equals AI. This gives us the following expression. Since A1.A2 equals A2.A1, we have G12 equals G21, which means this can be represented as a matrix. Using Einstein's summation notation, the inner product of contravariant basis vectors. We express the inner product of contravariant basis vectors as follows and call it the contravariant metric tensor. A dot bi equal AI. From this, also since b1.b2 equal b2.b1, we have G12 equal G21. This can be written in matrix form or equivalentry. With the metric tensor, we can convert between the two types of components. This process is called raising and lowering indices. The dummy index J disappears through contraction, and the components are transformed. Relationship between the covariant and contravariant metric tensors. Let's substitute equation 2 into equation 1. As shown above, the product of the covariant metric tensor and the contravariant metric tensor yields the identity matrix. Let's perform the matrix multiplication. Gijgjk equals the Kronecker delta, where gjk equals gkj. This means that Gij and gkj are inverses of each other.